Sunam team, Abhilash PG, Anjan SR, Akash GP, Vaibhav GP, SK Karthik, and Nanu. Next please, Karthik. And here I am going to explain about an introduction to IoT and CoAP, impact of IoT, interconnected sensors, introduction to CoAP, and a RESTful design, system focus, real-time visualization. In the impact of IoT, Internet of Things has a transferred environmental monitoring by enabling a real-time data collection through interconnected sensors, leading to more informed decision making. In the interconnected sensor, utilizing a interconnected sensor allows for a comprehensive monitoring for various environmental parameters, enhancing the ability to respond the changes swift and effectively. And in part in 3, introduction to CoAP, the considered application protocol is a specialized protocol designed to the IoT, featuring a lightweighted architecture that supports efficient resource constrained devices. In a RESTful design, CoAP employs a RESTful design model, making it easier for developers to integrate and work with the web technology, allowing for seamless communication between devices. And system focus, this report focuses on the design and implementation of a CoAP based monitoring system that tracks light, sound, and motion, providing a valuable data for analyze. And in real time visualization, the implementation includes a web interface that visualizes the data in a real time, allowing users to monitor environmental conditions continuously and make timely decisions. And next slide. And understanding CoAP RESTful architecture, resources such as light and motion are accessible using, you know, HTTP like methods, enabling an intuitive interaction model for developers. And lightweight design, COP operates over UDP with minimal overhead, making it a deal for resource considered constrained devices and low power networks, ensuring efficient communication reliability. The protocol implements a transmission and in conjunction control mechanism to effect efficient manage data transmission over loss networks, enhancing reliability. Observation, COP supports the server push notifications, allowing sensors to notify clients of a data changes without the need for a constant polling, reducing network traffic. And this is going to explain about further.
I am explaining about the system architecture, overview of key points and network design. First one in that sensor node. These are the critical components that collect environmental data such as light intensity, sound levels, and motion detection through various sensors including LDR TSL 2561 microphone modules and PIR sensors. And second one is microcontroller. Microcontroller manages the data from the sensor node and facilitate communication using CoAP devices like ESP32 or ESP8266 are referred to their Wi-Fi capabilities. Third one is gateway. A gateway acts as a bridge aggregation data of sensor node and forwarding it to a cloud database or local service. Typically, devices including Raspberry Pi and similar alternatives. And fourth one is web interfaces. A user-friendly web interfaces is essential for displaying the sensor data and facilitating analysis. Technologies such as Flux or Node.js for the backend and or Chart.js for the front end are commonly used. Fifth one, network design. A network employs a star topology where sensor node communication directly with a central gateway. The communication protocol involves CoAP for a local connection and HTTP and MQTT for the interaction with the cloud. Next one is implementation steps. Implementation steps. A breakdown of the integration and communicational process. First one is sensor integration. Connect sensor to microcontroller and develop firmware to effective process both analog and digital signals received from the sensor. Second one, CoAP communication. Utilize libraries such as lib CoAP or CoAP thon to facilitate restful interactions. Config resources for parameters like intensity, sound levels, and motion detection. Third one is gateway and server. Set up a gateway that bridges CoAP with HTTP MQTT protocols to enable smooth data transfer and storage in database such as SQLite or MongoDB. The fourth one is web interfaces. Developing a backend system to manage data retrieve and API integration alongside a frontend that visualizes data through graphs and tables using chart.js for intuitive understanding.
Now we are talking about the advantages and challenges of CoAP, understanding the benefits and obstacles of CoAP implementation. Uh, the first advantage is efficiency. CoAP is designed for low power consumption, making it ideal for resource constrained devices in IoT environments. Second one, scalability. Supports IPv6, allowing CoAP to scale effectively for extensive sensor networks, accommodating a vast number of devices. Real-time updates. The observation mechanism in CoAP provides real-time notifications, ensuring timely data updates from sensors. Energy constraints. Battery operated sensor nodes face energy challenges, particularly in data transmission, sensor operation, and processing. Next on data transmission. Wireless communication in energy intensive, especially during retransmissions caused by packet loss, impacting overall battery life. Sensor operation. Continuous monitoring activities such as sound or motion detection led to increased power usage in sensor nodes. Microcontroller processing. Frequent computations in microcontroller can quickly deplete battery resources, necessitating efficient processing strategies. Mitigation strategies. Implementing strategies like duty cycling, sleep modes, and efficiency protocols can significantly enhance battery life. Duty cycling. Activating sensors and communication models only during necessary intervals helps to extend battery life considerably. Next one, sleep modes. Microcontrollers such as EP, ESP32 can enter deep sleep modes to minimize power draw during idle periods. Last one, efficient protocols. CoAP's lightweight design minimizes overhead compared to HTTP, leading to reduced energy consumption during data transmission. Network congestion and scalability. Understanding challenges and solutions in dense sensor networks. First one, network congestion factors. Congestion in dense sector networks mainly result from limited bandwidth and stimulates transmissions from multiple nodes, leading to dark packet loss and delays. Congestion control algorithms. Constraint CoAP advanced improves network efficiency by dynamically adjusting retransmission timers based on real-time network conditions, crucial for handling heavy traffic. Prioritization of critical data. Assigning higher prioritizers to critical data types such as motion detection alerts, ensuring their timely delivery amid congestion, enhancing overall system responsiveness. Scalability challenges. As the number of nodes increase in sensor networks, resource management and timely communication become increasingly complex. necessitating effective solutions. IPv6 and CoAP integration. Integrating IPv6 with CoAP allows support for a virtually unlimited number of devices, addressing scalability challenges and facilitating more extensive network development. 6LO WPAN benefits. Leveraging 6LO WPAN technology enables low power wide area networking, making it easier to connect numerous low power devices effectively in sensor networks.
Security in CoAP systems. Understanding vulnerabilities and mitigation strategies in CoAP. In eavesdropping, unencrypted data transmitted via CoAP can be intercepted by malicious actors, leading to unauthorized access to sensitive information. Next, spoofing and injection attacks. Attackers can manipulate sensor reading by injecting false data or implementing legitimate devices, compressing the integrity of the system. Next is datagram transport layer security, that is DTLS. DTLS provides an essential encryption for communication between nodes and gateways, safeguarding the against data breaches and ensuring the privacy. Next is authentication. Implementing the robust authentication mechanisms ensures the only authorized devices can join the network, significantly reducing the security risk. Next is applications of CoAP based monitoring systems. Significance of CoAP based systems. CoAP enables the efficient communication in resource constrained environments, making it ideal for various monitoring applications. And next is smart cities noise pollution monitoring. Sound sensors gather decibel levels to identify noisy areas, supporting urban planning and regulation enforcement. Smart cities dynamic lighting control. This explains the light sensors access ambient brightness, while motion sensors detect activity, facilitating adaptive street lights that conserves energy. And agriculture crop growth analysis. This makes the light sensors monitor sunlight exposure, optimizing irrigation and fertilizer schedules to enhance the crop yield. Next is agriculture pest and animal detection. Motion sensors identify the threats to crop, triggering alarms or sprinklers to mitigate the potential damage. Next is industrial safety, hazard detection. Sound sensors detect the abnormal noise level, indicating the machinery malfunction, while motion sensors monitor restricted areas to prevent the unauthorized access. Next is disaster management, environment monitoring. Networks of sensors can monitor environment changes, detecting the indicators or earthquake and floods for timely alerts.
Developments are underway for CoAP to improve efficiency, including CoA Plus, which introduce adaptive retransmission timers and conjunction control, optimizing performance in dynamic environments. Integration with edge computing, local data processing at gateways or sensor nodes, minimize bandwidth use and latency. Exemplicity for motion sensors that evaluate moment significance before altering gateways. Hybrid communication protocols. Combining CoAP with MQTT enhances system scalability and reliability. Using CoAP for power efficient sensor communication and MQTT for effective cloud data transmission. AI and predictive analytics. Incorporating machine learning into IoT systems allows for predictive insights, such as using data patterns to forecast weather or human activities. Narrowband integration. Narrowband technology significantly extends sensor network ranges, making it ideal for applications in agriculture and disaster monitoring, ensuring low energy connectivity over great distances. The practical development and conclusion. Hardware section. Choose sensors that ensure accuracy, durability, and low power consumption. The ESP32 microcontroller is recommended for its dual core processing capabilities. Field testing. Extensive field testing is essential to evaluate signal range, under various environmental conditions and ensure data integrity for accurate data collection and transmission. Maintenance practices. Regular firmware updates are crucial for enhancing performance and security. Implement a battery replacement schedule based on duty cycle estimates and secure and ensure uninterrupted operations. Conclusion of findings. The CoAP based environmental monitoring systems amplifies the transformative potential of IoT in industries and urban infrastructure, promising enhanced efficiency, scalability, and intelligence. Challenges to address. Key challenges such as energy efficiency and insecurities need to be addressed to ensure a robust and reliable solution for real world applications. Thank you, everyone.
The backend built with the Flash and used the CoAP Python library to fetch the environmental data for light, sound, and motion. From CoAP enables a sensor node. It provides their RESTful endpoint, light, sound, motion that results real-time sensor data in JSON format. Flash CORS enables the cross-origin request, allowing the format to communicate with the backend simultaneously. For front end is an HTML based on the dashboard that uses the charts.js for real time visualization of the light and sound data. It fetches the data every 5 seconds from the backend RESTful APIs and the updates the charts dynamically. Motion status is displayed as a text file on the dashboard, ensuring clear and user-friendly monitoring of the sensors. I will execute this code for backend. Run code. Run code, and we get a link. We will copy this link. We will paste this link here and enter. We get an endpoint of light, sound, and motion, and we will for every each code this for light. We get light mock data for light, and as uh, for sound, we get same as chain and light mock data for sound, and motion get same as per back. Motion data for data for motion. Artilal. We get successful this code. I will go back to the code. We get successfully execution in web interface. We get this output. For front end HTTP, we use HTML. We will run this code. We get this dashboard for environmental monitoring dashboard, light sensor, sound sensor, and motion sensor. In here, we will get real-time data will displayed in this.